All right, this chapter is about gases, but in order to understand gases, you've got to know something about pressure and what pressure is, okay? So, if I took a bowl of water, okay, like this, say if I had a bowl of water like this, right, full of some purple water, let's say, and I took a test tube, a very long test tube, full of water, all right, and I inverted it into the water. All right. And you could try this at home. The test tube is already full of water, so you would get something that would do something like that. If you're very careful, you might get something that's, near the end of the test tube. All right. So there's a certain weight that this purple water has. There's all purple water in here. This is open-ended at the bottom, and this is all purple water that you have. Okay. And you can try this at home. You can try this at home with a tall glass. In a tall glass, you could put like a card under, like maybe one of those coasters. You could put a coaster underneath the glass, and you can put it in a, like a Pyrex bowl so you can see what's going on. You could do it in a cereal bowl too, full of water, okay? And then you could slide out the coaster, and what will happen to the water? Will the water press down on this, and the water will go coming out of the bowl, okay? If you try that at home, it'll just stay stationary like that, okay? And in fact, you can have a really, really, really tall glass. If you get like one of those big old Pilsner glasses, that they drink in those fancy bars, and you do the same thing, okay, and you invert it full of water, the water still won't come out, okay? Does anybody know why that happens the way it does? How come the water just doesn't come down and press on this water right here, and it goes and it spills all over the place? Well, there's something called atmospheric pressure, okay, that we all live in. Atmospheric pressure exerts a force down on this water, like this, right? And you're not aware of it because you were born under regular atmospheric pressure. You think, there's nothing around us. But in reality, what happens is your body lives in a soup of gases, a soup of nitrogen gases and oxygen gases and trace amounts of others. And all of these gases are particles that float around, and they're under a certain amount of pressure. And the reason why the water stays in the test tube, or even a very, very tall glass, is because of the atmospheric pressure that's pushing down on this. Okay, so in fact, if you had a glass or a test tube or whatever that was, let's say if this distance right here and this distance right here, the distance between the water level and where the end of the water level is in the test tube, if you made the tallest one that you could possibly make, if you made it 10.3 meters, that would be the limit, okay? If you made it taller than 10.3 meters, then the water, this wouldn't be true anymore, okay? So 10.3 meters is the limit because atmospheric pressure is only so strong. If I make this incredibly tall, then the water is going to start to fall out, okay? That's with H2O, okay? That's with H2O. I'll have a maximum of 10.3 meters for the tallest level of water that I can have. But there are denser liquids that are available to you on the periodic table. Denser liquids than H2O. So let's pick a denser liquid than H2O. A much denser liquid than H2O is this symbol right here. What does this mean when I write this? Mercury. What do we know about mercury?
Liquid metal.
It's liquid metal. It's the only liquid metal that we have at room temperature, okay? So if I took this, test tube and I started marking it in millimeters, all right? And if I measured the distance from here, now this is no longer water, this is all mercury. I've swapped out the water, I've emptied all the water out, and all the purple stuff that you see here is all mercury, okay? Now if you do this kind of thing, you got to be very careful because mercury is poisonous. It gets into your skin, does bad things. But anyway, if you do this, okay, the mercury will stay at a certain level. And what is the number of millimeters that I'll measure? Do you know? It'll be 760 millimeters if I measure that. Okay. So that's where we get 760 millimeters Hg. 760. It's 760 millimeters of Hg or mercury in that tube. Okay, under a condition called 1 atm, which is 1 atmosphere of pressure, and that's the pressure at sea level. Okay, of course, if you go up to the mountains, this pressure is going to go down. It might be 752 or 750 or whatever. If you dive into the ocean, this could be several times 760 millimeters Hg. This could be 1400, 1500 millimeters Hg for the pressure. Okay, so in fact, this is the way that Torricelli actually came up with Torricelli lived many, many years ago. He's an Italian scientist. And this was the very first experiment that he did to discover atmospheric pressure. So that's where the millimeters Hg comes from. It's known as 1 atmosphere, 760 millimeters Hg. So there's some conversion factors that you should be familiar with. This is one of them. 760 millimeters Hg is 1 atmosphere. But guess what? This is also equal to 14.7 psi. Okay? 14.7 psi stands for pounds per square inch, and that's pretty amazing if you think about it. Yeah. All right. Okay, so 14.7 pounds per square inch is atmospheric pressure. If you think about it, that's pretty amazing, because think about what a square inch is. It's about the size of a postage stamp, right? Nobody sends anything in the mail anymore, right? But if you still do like I do, right? A postage stamp is about 1 inch square, right? Now think about postage stamps all over your body. Each one of those postage stamps is 14.7 pounds per square inch of pressure. You don't think that's any big deal because you were born that way. Everybody was born that way, and that's. But if you don't feel 14.7 pounds per square inch on your skin anymore, that means you're in outer space and you're not going to live very long, because the body needs that minimal amount of pressure to stay alive. Now there's a range, right? You could dip a little bit below that. You go on board an airplane and some of the pressure will dip, because when an airplane goes up in altitude, that cabin that you're in, when you're flying from BWI to Los Angeles or whatever, that cabin that you're in, as you take off, as you're up 30,000 feet up in the sky, that's a pressurized cabin. It's pressurized at 14.7 pounds per square inch, because the outside pressure at 30,000 feet altitude is much lower than 14.7 pounds per square inch. And you won't live very long outside. You have to be in that kind of environment. So we take it for granted because we were born in that pressure, but and then there's one more conversion factor that you got to know for this chapter, and it's this. These are all equal to 101 3025 newtons per meter squared. So those are 3 conversion factors for pressure. All right. Let me get right into something called kinetic molecular theory. Of gases. I'm only going to talk about gases. There's 3 states of matter, right? There's solid, liquid, and gas. I'm only going to be concerned with gases for this topic, all right? Now, the molecular theory of gases has a certain model, okay? And sometimes in engineering and science, we use models because they have nice, simple ways of looking at things. The model for this has certain assumptions. So we have to make certain simplifying assumptions. And these are good to know, okay? And what I'm talking about is I'll draw it on the board for you. I've got some kind of container, right? that's closed at the end, and it contains, some type of gas, right? These little purple particles right here indicate that I've got some type of gas, and it's closed, the lid is closed, and that gas occupies a certain volume, and there's a certain amount of that gas in there, okay? So the gas contains particles, and one of the assumptions is that the particles are in motion, are in constant motion. The second assumption I need to make for this model to work is that there are no attractions or repulsions among the particles. In reality, there is. In reality, some of the particles might have a repulsion or attraction, but in order for this theory and in order for this model to work, I'm assuming that when that purple particle gets real close to that purple particle, there's not some kind of mysterious force that's repelling them or attracting them. I'm just assuming that they're tiny little particles that don't have any charge. So if you don't make this assumption, this model doesn't work. All right. Another assumption you have to make is that there is a lot of space between particles. Unlike a solid or a liquid, gases have a lot of space in between the particles. And then one more assumption that you have to make is that the speed of the particles increases with increasing T. And increasing T means temperature. So if I have in the laboratory, the chemistry laboratory, you've got this thing called a Bunsen burner, and it's got a little, there's a spigot in the laboratory that you hook this thing up to, and it's got a little hose that you connect up here, and then you light a match, and it generates a flame. The flame is not red, but I'm just putting it in there so you visualize it as a flame. That's a Bunsen burner. If I do that in the laboratory with a Pyrex sealed container full of some gas, what I'm doing is I'm adding heat to it. Heat is a form of energy. Right? So when I'm adding heat to this closed container, the particles start whizzing around at faster speeds. The speed of the particles increases with increasing temperature. So if I increase that temperature, I'm giving more energy to the particles, and they're going to whiz around much, much faster. Right? There are also certain, there are also certain facts about gases. One of them is that the gases are compressible. Another one is that the gases assume the volume or shape of the vessel they are in. So with that cylinder that I've drawn, the gas is going to occupy, the gas particles are going to be as far apart as they can be, but they're going to occupy the entire shape of that cylinder. Okay? And the last thing that's a fact about gases is that they have low density compared to liquids or solids. Okay. So those are all the things that you need to know about gases. They have low density compared to liquids or solids. Okay, so that's everything, and it's good to know this stuff, so jot that stuff down. I'll have it on the video when I post it up on YouTube. All right. Let's go to the third subsection that we're going to talk about. I'm going to keep my little picture of the container full of gases here. What I'm going to do, I'm going to talk about pressure. And pressure involves constant molecular collisions. So you can tell, if I've got this at a certain temperature, these little particles are whizzing around. So I'm going to give them little tails to indicate they're whizzing around. And they're all whizzing around in different directions. They're not all following the same direction. So they're all whizzing around in that closed container. All right? There's a basic formula for pressure that you need to know. And by the way, pressure is always indicated as capital P. All right? And it goes like this. The pressure is equal to the force per unit area. Okay? And if you think about it, okay, if I have a force, and in the good old U.S. customary system, one of the units for force are pounds, right? Pounds of force. And then the area, okay, is actually inches squared, right? Square inch is a form of area. That's why we say pressure on the side of your tire when you go fill your tire up, or when it's low, we say you have so many pounds per square inch in your tire. That's exactly what it's following, this formula. It's following the formula of force per unit area. Okay, so what area are we talking about? Okay, well, for the moment, let's erase the Bunsen burner. All right, we're not heating this up. We have a certain gas. Even when the gas is at room temperature, those gas molecules are moving around, so there's a certain pressure involved. Okay, but what I'm going to do is I'm going to add a piston to this thing. All right, so I'm going to put a big old piston in here. Piston right there. And this piston is able to move up and down. So I'm able to squash those molecules if I want to. And when I'm squashing those molecules, I'm messing with the volume. Okay? So the force, where is the force coming from? That variable right here, F, okay, is the force that I'm putting down on that plunger. Whatever it is, if it's a human hand or if it's a machine or something, pushing down on that plunger, squashing the gas. That's where the force comes from. Well, where does the area come from? The area can be measured, let's say if this is I didn't draw this real good, let's say if this is a perfect cylinder, right? Like the one you see in the textbooks. That's as perfect as it's going to get. Okay? And that cylinder has a certain radius called R. You can measure that. You measure whatever the diameter, take half the diameter, gives you the radius. Okay? Well, the area, okay, for that cylinder is actually going to be equal to what? It's going to be equal to pi r squared, because that's the area of the circle. So the area down here should be exactly the same as the area up there if it's a symmetrical cylinder and the piston is airtight with it, right? So you measure whatever the diameter is, take half of that, that's your radius, you plug it into the formula, and that's your area. And again, that force has units of pounds, and the radius has units of inches, so it's inches squared. So that's where pounds per square inch comes from. So I just explained what the area was for pressure. This is always, always, always used, for an example of pressure. Now, in the scientific system that we used, the Système International, right, or the metric system, the units, okay, so in the SI system, the units are going to be instead something called newtons. We represent newtons by capital N. And the area is going to be represented by meters squared. Okay, that's a meter squared. So the pressure in the SI system is going to be newtons per meter squared. All right, so there is a convenient way of representing this. When I say something has so many newtons per meter squared of pressure, there is a convenient compact way of representing this. This is called the Pascal. That's what the unit of Pascal comes from. Okay? Don't forget that 1 atmosphere of pressure is equal to 101 3025 pascals, or you could write it like this, 101.325 kilopascals. That's 1 atmospheric pressure. Another unit that I said you should know is also, 760 millimeters Hg, which is also equal to 760 torr. Why is it torr? Because the guy who came up with that, his name was Evangelista Torricelli. So Torricelli was the Italian scientist who actually came up with that inverted mercury in the pool of mercury, and that's called a barometer. Barometer is a device that measures the atmospheric pressure. That's the first barometer that Evangelista Torricelli came up with. Okay, so all of this might be confusing the first time around. Let's do a little simple example, okay? So, for example, 0.5 atmospheres is how many torr? All right, cute little example there. If I have 0.5 atmospheres, which is my given, I'm going to multiply that by a conversion factor, okay? I said that 760 millimeters Hg is equal to 760 torr, okay? So 760 torr is equivalent to how many atmospheres? One atmosphere, right? One atmosphere. All right, and this is just a units conversion problem, right? So the atmospheres go away. I'm left with so many torr. So that's basically saying 0.5 times 760. That's going to be equal to 360, right? Oh, 380, you're right. 380 torr. And that's pretty much everything you need to know about pressure. We're going to be talking, I'm keeping this cylinder up here for a reason, because we're going to be using this quite a bit. I mentioned the big P, pressure, right? And there are two other variables that we're going to mess with in this chapter. We're going to mess with volume. So you should know how to figure out the volume of the cylinder, right? The formula for the volume of the cylinder is just simply you take that pi r squared, which is the area at the back end, and you multiply it by what? No, you multiply it by the height. That's all there is to it, right? So the volume is actually pi r squared times the height. And that's the volume of any cylinder that you want. Whatever that height is, find out what the radius is on the bottom. Pi r squared times the height will give you the volume. The other variable that we're going to have to know is the temperature. Right? So when we talk about temperature in this chapter, you're going to have to know degrees Celsius, you're going to have to know degrees Fahrenheit, and you're going to have to know a third scale called the Kelvin scale that we talked about earlier. Okay? So these variables, volume, temperature, and pressure, PV and T, we're going to be discussing in detail. But for now, that's everything you need to know about pressure. Let's talk about Boyles Law. Boyles Law sounds like a big deal, right? You hear about something called a law, it sounds like a big deal. It's really not a big deal. It's a very simple relationship. It's a relationship between volume and it's a relationship between pressure, 1 over P. If I write this symbol like this right here, that's the Greek letter alpha, lowercase alpha, right? Greek has uppercase and lowercase letters. You won't just see this in your book, you'll see this in any mathematics or science book that you ever pick up. When you read this, okay, this is a shorthand way of saying that proportional to, that's what alpha means. It means proportional to. That means whatever the volume is, okay, it is proportional to 1 over the pressure. The best way of saying this is that the volume is inversely proportional to the pressure, okay? So volume, and we say inversely proportional because I've got 1 over. So that being said, right, there's a certain state 1 that I'm in and a certain state 2 that I go to. And it's true, you could go to state 3, state 4, and state 5 or whatever, but we're just dealing with 2 states. So that being said, we use these special little subscripts to indicate P1 times V1. That means I'm in state 1. I have a certain pressure and a certain volume in state 1. But since PV is always a constant, and all the subscripts mean is that I'm in a certain state. That's all it means. So I have a certain pressure and a certain volume. That's equal to a constant. But if I go to state 2, I'm going to have whatever that state 2's pressure is. I'll have P2 V2. Remember, whenever I take any kind of pressure for a certain gas, for hydrogen gas, you have to pick the specific gas that you're dealing with. Whenever I have a certain pressure of that hydrogen gas and a certain volume, there's going to be a certain constant that corresponds to that hydrogen gas. Well, guess what? That means that this is equal to this. If I'm in state 1, I've got a certain pressure and a certain volume. And pretend I haven't, squashed the gas, right? I've got it at maximum height. So you could measure the volume, and then I've got a certain pressure there. And the way you do that with a cylinder is there's a little pressure gauge that sticks out here, and it measures, so many pascals or torr or whatever you're using for pressure. So you measure the pressure that way, and the way you measure the volume is, you measure how far down the plunger is, and you know what the dimensions are of the cylinder. So you have a certain P1 and a V1. If I decrease that volume, decrease this number, okay, what happens here with P2? It goes up, right? So it compensates for it. So that's basically the heart of Boyles Law, and that's one of the first gas laws that you learn. So let's do an example, all right? So for example, let's say we have P1 pressure, right, is equal to 4 atmospheres. And again, that doesn't have to be atmospheres. It can be torr, it can be millimeters Hg, whatever it is. Let's say P2 is equal to 1 atmosphere. If instead I wrote 760 millimeters Hg, you would have to be smart enough to know that 760 millimeters Hg is 1 atmosphere, because the pressure units have to be consistent. So in other words, you have to convert it so that you have consistent units. So I got 4 atmosphere and 1 atmosphere here. And then the volume for state 1, let's say, is going to be 6.0 liters. And then the problem says, and this is very typical of the homework kind of problems, find out what the end state volume is. Right? So all you have to do is you have to use this relationship. P1 V1 is equal to P2 V2. Well, I have P1, right? I have a V1. Instead of saying equal to P2 V2, okay, what I'm going to do is I'm going to leave the V2 over here, but I'm going to divide through by the P2. All right, just a little bit of simple algebra. And now I've got a nice cute little formula that gives me the answer. It tells me what the V2 is going to be. So this is the part that everybody loves, right, the plug and chug. So we put in 4 atmospheres here, times the volume, which is 6.0 liters. Divide that by the second pressure, which is 1 atmospheres, right? And then you can see we've got the atmospheres cancel, right? The units, always get in the habit of being disciplined to, make sure that you treat the units as individual numbers. And then you wind up with what? The V2 is going to be what? 24 liters, right? So think about it. What did I do? In state 1, I had 4 atmospheres. In state 2, I had 1 atmosphere. I decreased the pressure. Now, I want you to think about it intuitively. If I decrease the pressure, what happens to the volume? Volume goes up, right? Did the volume go up? Yeah, we went from 6 liters to 24 liters. So that's a way you could check these problems, right? You could use common sense to figure out if that's the case. So that's Boyles Law. Boyles Law establishes a relationship between volume and pressure. All right? So let's erase that. Let's do another one. Let's do Charles' Law. Charles' law, very simply stated, says that the volume is proportional to the temperature. That's all Charles' law says. So I think you can see where I'm going to go with this. I can divide through by the temperature. So volume over the temperature is actually equal to some constant. All right. So now I'm definitely going to use a Bunsen burner, right, when I talk about Charles' law. Imagine I don't want to erase the equations, but imagine I have my Bunsen burner here, and I'm lighting this up, or I'm taking it away when I want to cool down the gas. So in other words, I'm going to mess with the, oh, by the way, when I have Boyles' law, go back to Boyles' law, I have to hold something constant. The temperature is constant. Remember, when we just talked about volume and pressure, there's an underlying assumption here that the temperature is constant. For Charles' law, I'm messing with the volume and the temperature, and I can only do that when the pressure is constant. All right. But when I take this ratio of volume to temperature, that gives me a constant. This is not to be confused with, this being equal to pressure or something. That's not what I'm saying. I'm saying when you take this ratio, it equals a certain number, a certain constant. So that being said, I can write Charles' law like this with the states. I go from state 1 to state 2, and this state idea applies to Charles' law as well. I have V1 over T1 is equal to V2 over T2. Okay, now I want to write down an important note. Don't ever forget this. Okay? The T must always be in Kelvin. That's the only way that the gas laws will work. You must have the temperatures in Kelvin. In other words, if I put a temperature of Celsius here, you get the wrong answer. If you put a temperature in Fahrenheit here, you certainly get the wrong answer. They must be in Kelvin. So just as a little reminder, okay, these are the ways that you convert to Kelvin. The temperature in Kelvin, you always get the temperature in Kelvin starting out with the temperature in Celsius. And you add what? 273.15. That's a conversion factor you should never, ever, ever forget, okay, especially for the final. So the temperature in Kelvin is the temperature in Celsius plus 273.15. Well, let's say if I was really mean to you and I gave you a temperature in Fahrenheit, right? Well, how do I do that? Well, there's no direct way of doing that. What you have to do is you have to have a relationship between Fahrenheit and degrees Celsius. And here you need a second formula for that. The temperature in, the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. 1.8, you might see some books that say 9/5. You take 9 divided by 5, you wind up with 1.8, right? So 9/5 Tc plus 32 or 1.8 Tc plus 32, that will give you the temperature in Fahrenheit. So you have to do some algebra, right? If I say the temperature is 20 degrees Fahrenheit, then you have to do some algebra to manipulate this, right? So if I do the algebra, I get Tc is equal to what? Tf minus 32 divided by 1.8 if you do the algebraic steps, right? Bring the 32 over the other side, but you got to divide the whole thing by 1.8, and that's the relationship. So say if I give you 20 degrees Fahrenheit, well, 20 minus 32, you wind up with a negative number, right? That's true because it's a very cold temperature, right? 20 degrees Fahrenheit. So you wind up with the temperature that's cold for temperature in Celsius. I want you to think of one other thing, an example. So I'm not going to do a piston, but I'm going to do a balloon in ice water. Say if I've got ice water, right? Ice cubes floating around. And I've got a balloon, right? A balloon that I took from a regular room temperature, right? If I take a balloon from regular room temperature, what's going to happen to that balloon is he's going to shrivel when I dunk him in the ice water for a few hours. Now look at this. If I take that same balloon and now I have boiling hot water, right? And what's going to happen to the balloon? The balloon is going to expand, okay, to its full volume. That's what's going on here with Charles' law, all right? The volume is directly proportional to the temperature, all right? What happens when I lower the temperature? What happens to the volume? It goes down, right? What's happening to the volume in the balloon? The volume in the balloon is going down when I lower the temperature. This is cold, right? Low temperature. If I go in the other direction, if I increase the temperature, then the volume is going to expand, right? So these are basic laws of nature, okay, that apply to gases. So that's a good little example that you can stick in the back of your head for, thinking about these problems. And I'm going to capture that formula over here as well. All right, I'm going to move on to the next section. So this is Charles' law. And it says that the volume is proportional to the temperature with constant pressure. Now I'm going to do section 6, which is the combined gas law.
Is this where Charles meet Boyles?
Well, no, this is, yeah, exactly. This is where they meet, right? This is why, yeah, it's a good observation. So yeah, this is the whole reason why I put this up here, right? The volume is proportional to 1 over the pressure. That's Boyles' law. Charles' law is the volume is proportional to the temperature, right? So just like he said, I'm going to put these things together, all right? So it turns out when I put these two things together, I can write, this is volume is equal to 1 over pressure, volume is equal to temperature. So what I can do is I can say that the combined gas law is pressure times volume over temperature is equal to a constant. So that's interesting, right? Pressure times volume, that's when I do the P times V, that gives me a constant, right? And I said that V over T is a constant, so I'm putting these two facts together, and now I've created something called the combined gas law. It's where I've combined Boyles' law and Charles' law together. And again, with the states, going from state 1 to state 2, you can do the same thing. P1 V1 over T1 is equal to P2 V2 over T2. So in fact, you can kind of forget Boyles' law and Charles' law because the combined gas law gives you everything you need. Well, you might say to me, well, that's not true because what happens if the temperature is constant? Well, if the temperature is constant, that means that this T is equal to this T, right? Imagine instead of saying T1 and T2, just saying T, right? Then that side will cancel that side, and that goes away, and what do I get? I get Boyles' law, right? P1 V1 is equal to P2 V2. Well, then you might say, okay, well, how about Charles' law? Well, same thing. Charles' law is at constant pressure, so instead of saying P1 and P2, all right, say if I just have P, then the P goes away, and imagine that, and the P goes away, then I've got V1 over T1 is equal to V2 over T2. That's just a statement of Charles' law, okay? When I'm holding certain value constant, I get that. Okay, and that's all you really need to know about that. So I'll write it down here, combined gas law. I'll just say combined. And I'll just do it like this, PV over T is a constant. 7 is another law. This one is known as Avogadro's law. Avogadro's number is, right? Avogadro is a number, Avogadro's number says 6.022 times 10 to the 23 particles is equal to 1 mole. So Avogadro's law has to do with the number of moles. It says that the volume is directly proportional to the number of moles. And this is not to be confused. You don't put in 6.022 times 10 to the 23. Don't be tempted to do that. This is an integer number. This means 1, 2, 3, 4, 5, 6 moles, right? And we know that a mole is 6.022 times 10 to the 23 particles, right? But 1 mole, 2 mole, 3 mole, that's the number that you use here. So this says that the volume is directly proportional to the number of moles. Now, imagine you have, I won't draw a picture up here, but imagine you have a little boy blowing a balloon, right? And the gases that are coming out of his mouth are carbon dioxide primarily and some other gases, right? But these can all be modeled using the molecular theory of gases. When he blows a little bit, he's got the balloon a certain, dimension. It's small. But when he blows more in, what is he doing? He's adding more particles into that balloon. That is what the number of moles are. He's adding more and more and more particles. What happens as he's adding more and more and more particles into the balloon? What is the effect on the volume? The volume increases, right? It kind of makes sense. And you see that balloon getting bigger and bigger and bigger. If the boy gets tired and he lets the air out, what's happening? He's letting the gas particles out of the balloon. What happens to the balloon? The balloon decreases, right? So as I decrease n, as I decrease the number of moles, the volume will also decrease. So this is also saying that the volume is directly proportional to the number of moles, or the number of particles. And again, we could write it with the states, right? You could say V1, well, so basically you say V over N is always a constant. And then with the states, you could say V1 over N1 is equal to V2 over N2. Assuming that everything else is fixed, assuming that the pressure is constant and the temperature is constant, that's the only way you can play this game, right? So pressure and temperature have to be constant in order for Avogadro's law to work. Okay? So let me write that down. It's Avogadro proportional to the number of moles. And that's all there is to it for Avogadro's law. All right. So far we talked about Boyles Law, Charles' Law, the combined gas law, which combined Boyles and Charles' law, and then we talked about Avogadro's law. There's finally one more called the ideal gas law. The ideal. Using the ideal gas law, we combine all of these other laws, including Avogadro's. And when you do that, you find out that the volume is proportional to the number of moles times the temperature over the pressure. I know I haven't gotten to the volume yet. We'll do that in a second. No, actually we have. The volume is proportional, so we have all the variables. Okay, we talked about volume and pressure in Boyles' law. We got volume and pressure. We talked about Charles' law, volume and temperature. There it is. The combined gas law is just a combination of those other two, so we got it. Avogadro's law talked about the relationship between volume and number of moles. So we've got all of these guys, Boyles' law, Charles' law, and Avogadro's law, included in the ideal gas law. So it is another combination kind of law. So it turns out that the volume on the right, okay, is always greater than the value on the left. Okay, so you can't do this. You can't say volume is equal to N times T over P, because when they did this so long time ago with the gases, they said, oh man, whenever we measure the number of moles of a gas at a certain temperature and a certain pressure, we get a number, and that number is adjusted by a certain factor. It's not always equal to volume. So you can't write this, okay? But I'll tell you what you can write. So you can't write that. What you can write is this. The volume is equal to Rn times the temperature over P. Okay, what is R? I'm getting tired of all these letters, right? That's what you're saying, Professor Jim, right? R is nothing more than a constant. It's known as the ideal gas constant. So R is the ideal gas constant. And that's how they got it. When they did the measurements in the laboratory, they measured the number of moles at a certain temperature and a pressure, and it didn't come out to be that volume. So they have to adjust it by an adjusting factor. And they repeated the experiment for different gases, for different volumes, temperatures, and pressures. Think of all the different, combinations and permutations, and you always get this same exact number. It's known as the ideal gas constant. It's a constant of nature, okay? It is 0.0821, and it has a bunch of funky units. Liter times atmospheres divided by moles Kelvin, all right? And that's what the ideal gas constant is. Now, the ideal gas constant will be different depending upon what kind of units you're using. If you're not using Kelvin, you're going to get something different. But the ideal gas constant almost always uses Kelvin. If you're not using atmospheres, you might get something different. But this is the ideal gas constant for these combination of units. All right? Why do I make a big deal out of that? Because if you look at this temperature better be in Kelvin, because it's got to match up with the Kelvin in the ideal gas constant. This pressure, right, has got to be in atmospheres. So you got to, if I give you a problem, or if your homework gives you a problem in pascals, you have to know how to convert from pascals to atmospheres, right? Same thing with volume. If you get volume in milliliters, you got to know how to convert to liters, and so on and so forth. Right? So that's the now. When you rearrange this stuff, there's a more common, version of this that you'll see in all of the textbooks. PV equals nRT, and that is really the ideal gas law that hundreds of chemistry students, and even physics, right? You see this in physics. PV equals nRT, right? You see T-shirts, geeky T-shirts at PV nRT, right? So that's a very famous, formula that's used over and over and over again in chemistry and science. So it says that the pressure times the volume is equal to the number of moles of the gas times the ideal gas constant times the temperature in Kelvin. And that always holds. That's the ideal gas law. Right? So again, if you're given a problem, right, that you have to figure out one of the variables, you'll always be given these things in terms of states. So you write it something like this. You do like P1, V1. It looks kind of like the combined gas law. Over T1, right, is equal to a constant. Well, that constant, if the number of moles of the gas are held constant, if I don't change the number of moles of gas, and it usually in most problems they are, guess what this is? This is the combined gas law. If you look at the combined gas law, it says PV over T is equal to a constant. Well, that constant, it turns out to be the number of moles of the gas times the ideal gas constant, right? And that's how you can use that to solve, 99% of your chemistry problems that deal with this. Now, to get the mass in grams for an ideal gas, let's say if you have a problem and they're asking you for the number of grams for an ideal gas, you have to have the formula weight in grams of that gas. So in those problems, in certain ideal gas problems, like on your homework, you might have to find out what the grams are for the ideal gas. And don't forget, you use your good old periodic table. You have to find the, F-I-N-D, the molar mass. The molar mass is nothing more than the grams per mole of the gas. So you know that from the periodic table. If I was dealing with hydrogen, which is the simplest one, right? He has an atomic weight of 1, so we know if I'm dealing with 1 mole of that stuff, it's going to be 1 gram. The same thing that we did before, right, with the molecular weights. Okay, so now we're going to talk about gases and chemical reactions. So it's always useful to do this kind of thing with an example. You might be familiar with this example. If I have H2 gas and it reacts with nitrogen gas, it's going to produce what?
Ammonia.
There you go. And ammonia's chemical formula is NH3. And it's a gas, We have to balance the chemical equation, so if you go through the procedure for balancing it, you put a 3 there and you put a 2 there. And we've got a balanced chemical equation. So let's do an example, all right? That's the best way to describe this section for gases and chemical reactions. Let's say if we're given, all right, a volume is equal to 2.5 liters. And we're also given the temperature. Temperature is 381 Kelvin. And then let's say we're also given the pressure. The pressure is going to be 1.32 atmospheres. And let's see, atmospheres. And that's the pressure of the H2 gas. That's what we're given. So using what I told you earlier about the combined gas law, all right, we're going to use the combined gas law. Remember, the combined gas law says what? It says PV is equal to nRT. That's the combined gas law. We can actually solve for the number of moles of the gas if you're given all that information. All right? So the number of moles of the gas, if you just rearrange the combined gas law algebraically, bring the RT up underneath this, you get PV over RT is equal to the number of moles. And we can plug in our numbers, all right? So 1.32 atmospheres is our pressure. The volume we said was 2.5 liters, and that's it for PV. R, okay, is equal to 0.0821, but don't forget the units is liters, atmospheres over mole Kelvin, and that's it for R. And then the temperature we said was what? 381 Kelvin. Again, get in the habit of, treating the units as numbers, as you should. The liters will cancel that, the liters will cancel that, the atmospheres will cancel, the atmospheres will cancel. The Kelvin cancels the Kelvin, right? And this is 1 over moles, so this jumps up to the top, right? And if you do all the calculation on your calculator, you get 0.1055 moles of H2. Oh, and I guess I should have told you what the question was. The question is, how many moles of ammonia gas are formed by hydrogen at a given pressure, volume, and temperature? So have I answered the question? No, because I've answered how many moles of hydrogen gas I've gotten. I haven't answered the question of how many moles of ammonia I'm going to get out of this reaction. So how am I going to do that? How are you going to help me get home here?
Create moles of hydrogen gas over.
Well, it'd be the other way around, right?
Oh, I'm sorry. Yeah. 2 moles of ammonia gas over 3 moles of hydrogen gas.
Right. Gas. See how I got that? He's just using the coefficients in the equation. That's how, just like we did, other examples like molar conversions. Now you're going to do this using the gas law. You're going to combine your knowledge of molar conversions with the gas law to get the answer. So and they're asking you, right, how many moles of ammonia are formed by this reaction of hydrogen and nitrogen, given a certain volume, temperature, and pressure. And that's a very typical question that you would get. So again, the units cancel. I got moles of hydrogen gas, moles of hydrogen gas. I do the math on the calculator, and what do I wind up with? I wind up with 0.070 moles of NH3, ammonia gas. So that's what section 10 is all about. All right. A little bit more on 10. All right. The last thing you have to know in this entire chapter is what this is, STP. What does STP stand for? Standard, right? Temperature, right? And what else? And pressure. All right, in order to utilize standard temperature and pressure, you need to know what the standard temperature and pressure is. So, what is the temperature going to be in standard temperature and pressure? It's going to be what?
This is going to be in Kelvin.
Doesn't have to be. I mean, you know, you can convert it to Kelvin to use it in the gas laws for sure, but it can be expressed like this: 0 degrees Celsius, which is equal to what? 273.15 Kelvin. Right? And then, what's the pressure going to be? What do you think the pressure is going to be?
1 atmosphere.
1 atmosphere, which is also what? 760 millimeters Hg, which is equal to what? 101.3 kPa, right? And there's a few others, right? Kilopascals. Okay, so now in your previous chapters, you should recall the following, okay? 1 mole of gas at STP, okay, 1 mole of gas at STP occupies a certain amount of volume. You know what that volume is? Any gas. That's a pretty amazing thing about this. You can take any gas. You can take 1 mole of neon gas, 1 mole of argon gas, even the diatomic gases. 1 mole of oxygen, 1 mole of nitrogen, 1 mole of chlorine. Pick your favorite gas, right? 1 mole of gas at standard temperature and pressure, which is 0 degrees Celsius in 1 atmosphere, occupies a certain amount of volume. It always, always, always occupies 22.4 liters. And that's a conversion factor you should definitely know. Okay. And then let me end it with some conceptual examples.
Hurry, your battery died.
It died? Okay.
And I said it's dying.
It's dying? Okay. Well, that's good because I'm almost finished. So, for example, 1 mole of helium at standard temperature and pressure. So you've got helium gas that's in this thing at standard temperature and pressure. The volume, what's the volume of 1 mole of helium at standard temperature and pressure?
22.4.
Yeah, just what I told you, 22.4 liters. But if you measure the molar mass, it would be 4 grams. 1 mole of helium at standard temperature and pressure. Now let's do 1 mole of xenon at standard temperature and pressure. I still have the same size box, right? And I got these molecules floating around. The volume is still going to be the same, right? 1 mole of xenon at standard temperature and pressure is going to occupy 22.4 liters. But what do you think the mass is going to be? Is it going to be the same? It's actually going to be much more. It's going to be 131.3 grams. Why is that? Why do I have different mass, in the same volume? I have the same number of particles. I have 1 mole. 1 mole is 6.022 times 10 to the 23 particles. So what's different about these things? What's that? The what? What are the particles? I couldn't. The amount of particles is the same, right? It's 1 mole here, 1 mole here. 1 mole is 1 mole.
They have different mass.
They have different sizes, right? So if you looked at this, if I was careful, right, and I drew this kind of to represent helium, helium is one of the smallest atoms there are, right? And you have these little helium guys floating around, right? But, and I drew 1, 2, 3, 4, 5, 6, 7, 8, right? So now I'm going to draw 8 xenon, right? 8 xenon guys are like this, right? 6, 7, 8, right? So I exaggerated it, of course, but xenon is actually much more massive than helium is. The volume is the same. I've got the same container. I've got the same number of particles. I have the same temperature and the pressure. The only thing that's different is the mass, right? So a mass of the xenon is actually, so that's a conceptual example for you for this chapter. All right. And that's everything you need to know about gases. All right. So,
Just.
yeah.
Right, yeah.
What about like water flowing through a pipe at a certain temperature?
That's hydraulics. Take my class on hydraulics. So that's all there is to it.